This is an example of parameter passing in C with a focus on the memory model of what's happening under the hood to implement parameter passing. We're going to use as our example a swap program to swap two variables, x and y. So here inside of main, in the main part of our program, let me get my cursor back here. So here inside of main, we've got our declaration of x and y with the values 3 and 5. So before the swap, we print them out, so we expect to see 3 and 5. Then we make the call to swap, and our intention is the 3 and 5 inside get swapped, and when we come back and print them out here, that we would get 5 and 3. That's our hope. And then here inside of the swap function itself, we implement the swap. We use a temporary variable, catch the 3, catch the 5, and actually do the swap. So that's what the program is doing. And let's take a look at what happens when we run this program. Here's the same program we were looking at a moment ago, and we run the program, and we get 3 and 5, and after we do the swap, there's still 3 and 5, so it's not correct. So what do we need to do? Well, right now these are being passed as value parameters, not reference parameters, and we could take a look at the model of what's happening inside of memory to explain what's happening here. So let's grab a model of memory and paste that in here that I got ready ahead of time for us. And in this model of memory, let me explain what we have. So memory starts at low address, so address 0, which is down here. And when you first turn the computer on, it's going to look at whatever's in memory down here, and that's going to tell it how to start off. So instructions for the basic operating system, and then the operating system in our case might be Windows, so we load up Windows, so that information is also in memory. And this part down here, by the way, might be mapped to a chip in memory to tell it what to do when it first starts up. So Windows is running, that gives us our environment. From within our environment, let's say we want to launch a program. Let's say the program we launch is Dev C++. Once we're inside of Dev C++, we start writing a program called swap, which is the program over here. And part of that program are these lines for x and y and the actual call to swap. So x has the value 3 in our sample code, right from over there, and y has the value 5 in our sample code. The other thing that will be helpful for us to think about are some addresses of where things are in memory, and we'll get to that in just a second. Actually, let's go ahead and put some numbers on these things right now. Notice that this is not to scale. It's imprecise in many ways, but it's just to get at some of the big ideas here. So let's say that we have some addresses in memory. 6, and of course this is not accurate, but something like this. And we actually want to see what happens when we make this call to swap, which is a function call. So first thing that happens is we're going to go off and call this function, but when we come back, we're going to go to the next line in the code, and in this case, after we do that swap, that would be this line right here. So we need to keep track of the address of that line. So we're going to store that on what's called the program stack. So this is the return address of where to resume execution. So it's just offset of one instruction away from the instruction where the call is made. So this would be at 2044 in this example. So the return address goes there. So the information as we make function calls, and function calls could call other function calls, this grows upwards in memory in what's called the program stack. And we will see later that, in fact, from the top part of memory, when we're dynamically allocating memory, and that would be done in using malloc in C or new in C++, dynamic allocation, that this is called the heap. And these two grow towards each other. You never want them to meet in the middle. If they ever meet, you get a divide overflow error, it's called, and and that's a problem. It crashes your program. So now, here's the stack. We're thinking about the details when we call swap. So the return address, which is what's the next line to go back to when we return from the function call, that gets put on there, and also the values for x and y. So what are the values for x and y? Well, we have a value for x, which is 3, and we have a value for y, which is 5, like that. So those get put onto the stack. Make it a little bigger so we can see it. And also locally here inside of the function we have a declaration for temp, so that would also be elaborated on the stack, some space for that. So roughly those are the things that we do. And the program's separately going to keep track of what line of code am I on as it continues executing the program. What's called the program counter would keep track of that. So we start executing this code up here at line A. Right there it says temp is equal to S. I'm sorry, these are not X and Y. These are S and T. They got renamed when we came into the function. And so the first thing at line A is temp is equal to S, so we get a 3 up there. So that's line A. And then line B, S is equal to T, so S is equal to T, like that. That's line B. And line C, T is equal to temp. There we go. Now if we were to print these out right now from right here within our function, we would see that the original values of 3 and 5 have now changed, and they are now 5 and 3. However, what happens when we run this program, when we come back now and resume execution at this line, which is this printf down below here, that in fact the change has not been made. So what's going on here? Well, what happens is that these values of 3 and 5 for x and y are local inside of main in here. And those are different than these values up here in memory. When we make the function call, this function call here gets its own local values. In fact, in this case, they're renamed. And those local values are not the same as these values down here. Changing the values up there is different. And we can see here in memory that, in fact, here's those local values. Those are changed, and these originals remain unchanged. So when we return back and do our print statement, we see that the values are unchanged. They started out as 3 and 5. We come back, they're still 3 and 5. So how do we fix this? And we have to, instead of sending value parameters where we send the values, we have to send reference parameters. And this involves sending the address of, in this case, integers, instead of sending the integer values themselves. So the code to do that, then, involves 3 things. So 3 rules for passing a parameter and having the change reflected back for a reference parameter. And these 3 rules are given here. We want to pass with an ampersand, we want to catch with an asterisk, and we want to use with an asterisk. So let's look at the code to do this and actually implement this. So here's our original code, and remember again that when we executed this code, that didn't work correctly. There was 3 and 5, and then we came back as also 3 and 5. So now we're implementing our 3 rules. So we want to pass with an ampersand. So we put the ampersands down here. We want to catch with an asterisk. So we catch with an asterisk up here. And then we want to use with an asterisk within the function where these parameters have been sent. So use with an asterisk, put an asterisk for each of these. Now if you had a long function, this of course would be somewhat of a pain. Something else that I like to do just to remind me of the type of variables these are is I put a P in front of it to remind me that this is a pointer to something and it's not the thing itself. There we go, like that. So now let's take this code and do the same exercise with the memory model and see how it's different when we're now implementing reference parameters. In fact, we should change it for good measure just to show that in fact 3 and 5, when we come back, they are now changed as 5 and 3. So let's take a look now at what's happening here behind the hood. So let's get our memory model, and in this case now, same sort of thing. We have the values for x is 3, y is 5. We call it, but now notice that we pass the address of x and the address of y. So we have an ampersand for these. So we don't, so first, the first thing that gets stored as before is the return address. And if we made the same assumptions, what are the values we had before? 2044, 46. So 2044, 2046, 2050, 2052. I believe that's what we had. Yeah, that looks right. Okay. So as we are implementing this function call right here, we first have the return address, which is going to be 2044, which is the next address to be executed when we return from the function. And then we also take the values of the parameters. So we sent x and y, and we're catching PS and PT. You could call it pointer to x and pointer to y if you wanted to. And the first one was x, the value 3. But when I sent it here, I'm not sending a copy of the value of x. I'm not sending 3. I'm sending the address. So what's the address of x? Well, that is this number, 2052. So that is what gets stored here, 2052. And then the second item to be sent is the address of y. And what is the address of y? That is 2050. So that gets placed here, 2050. And then again, as before, there's temp, which is elaborated on the stack, where we can store a temporary variable. And remember again, this is not to scale, right? There'd be lots more memory up here. And then we can start executing our instructions up here inside of swap. So instruction A is going to store something into temp. And what gets stored into temp? Well, I don't go to PS. What I do is every time I have the star is I use one level of indirection. So I use this as an address, and I go to that address. I dereference that address. Okay, so that's what that's going to be. So PS 2052, I dereference that address, so I go to 2052. That takes me down here. And what's at 2052? Well, this is what's at 2052. It's x, which has a value of 3. So by the way, inside of memory, it's not going to like have a little x there or anything. This is just, you know, symbolic representation of what's actually stored there. What's actually stored at that address is the number 3. So dereference PS 2052. I go to 2052. What's at 2052? The number 3. What do I do with it? I store it into temp. So number 3 gets stored into temp, like that. And now in instruction B, right here, it says dereference PT and store that into what's dereferencing of PS. So I take PT, I dereference that, and I store it at this address. So take what's at address 2050 and store it at what's address 2052. So what's at address 2050? It's at 5, and store it at address 2052. So it's doing this. And that's instruction B. And then instruction C, similarly take what's in temp, which is the 3, and store it into dereferencing PT. So PT is 2050, so the 3 is going to be stored at address 2050, and what's at address 2050 is this, so that 3 gets stored there. So notice that what's happened here is by using these addresses in this way, is that we are not changing these values in memory, but rather we're using them as pointers back to the original values, the original home, if you will, of where they are, and changing these in place. So the effect of this is then when we finish with all of this stuff up in the function, we go back to the return address, and we pick up execution right here at line 2044. That's our imaginary made-up addresses. It's going to use these local values for X and Y, these values, and it picks up these changes because the changes have been made in place by dereferencing memory. So the mechanism really is the same, that you pass a value up here into the function, and that value really is not being changed, but the fact that we use that as an address and go to that address and make changes there, that's the magic that lets all this happen. This is a little bit of a hassle with all of the asterisks up here and remembering to send with an ampersand. So in C++, the version of this is doesn't require all of those rules. In C++, all we have to do is add an ampersand in front of the parameter name in the declaration definition section of the function, which is much easier and makes us much happier.